let's continue our topic here. So now we're going to look at the relationship between the electric field and the magnetic field. These two things are exactly in phase with each other. They are also perpendicular to one another and to the direction of propagation like we saw in the last slide, okay? It is a transverse wave, therefore. So we have this diagram down here to show us exactly what I mean. I can give you a really helpful demonstration in class with this, but the basic idea is that if the electric field is along one axis, so in this case we can call this the z-axis, and this the x-axis. If the electric field is along the z-axis here, the B field will be along the x-axis. Okay, these are perpendicular to each other. Therefore, the direction of the wave, so what direction the wave will be traveling in, will be the y-axis here. Okay. Remember a few things about waves. When we go from highest point to the next highest point, that is called a wavelength. Okay. This is called the amplitude of the wave from highest point down to the axis. That's our amplitude. And so forth. But this is the main idea, that these three things are going to be perpendicular to each other: electric field, magnetic field, and the direction of propagation. Okay. We should also note that the ratio between the electric field and magnetic field strength in any electromagnetic wave is equal to the speed of light, c. So c is the speed of light, and it is approximately 3.00 times 10 to the 8th meters per second. Okay, so the speed of light is the distance that light travels, the speed that light travels, and we will see this a lot in our optics portion of the course. We will talk about the speed of light in different mediums, but for now, we're talking about in a vacuum. Okay, so in a vacuum, aka like space, there's no medium for these waves to travel through, so they're not slowing down. They are traveling at the speed of light, 3 times 10 to the 8th meters per second. Okay. All right, now let's talk about the energy in these waves. So these waves can bring energy into a system by their electric and magnetic fields, and these fields can exert forces and move charges in the system, therefore doing work on them. The energy carried by a wave is proportional to its amplitude squared. Okay, so if we have a larger E or B field, they will exert a larger force and therefore can do more work. So you can see it in these two different waves. We have some electric field and magnetic field here. They are producing some energy. This E is for energy, producing some energy. Therefore, we can see that if we have 2 times the amount of the electric field, 2 times the amount of the magnetic field, we will then have 4 times the energy, because it is a squared relationship. Okay. Now let's talk about the amplitude of the electric field and the magnetic field. It is going to be the maximum field strength. So what am I trying to kind of portray here? Basically, when we were looking at these lines here, so say that this is my drawing here, we had our magnetic field and our electric field. So this is our electric field. This is our magnetic field approximately, okay? So this is E, this is B. So our amplitude of these two, the highest point here to here, this is going to be my maximum field strength. And we will call that E naught. Okay. Same thing with this. My peak here for my magnetic field strength, my amplitude will be B naught, our maximum field strength. Okay. The energy carried and the intensity I in the electromagnetic wave is proportional to E squared and B squared. Continuous sinusoidal electromagnetic waves have an average intensity as so. So we have our average intensity here, where this equals C, our um, um, speed of light, times epsilon naught times E naught squared divided by 2. And because we know that E divided by B is equal to the speed of light, C, and epsilon naught is the same as 1 divided by, I should probably put this in parentheses here, mu naught C squared. We can also say it in a couple of different ways. Depending on the question asked of you, you may want to use some of these different forms, but they're the exact same meaning. So this I is the average intensity of the waves. Okay. All right, so since the waves are based on the assumption that the waves are sinusoidal, the peak intensity is actually twice the average. So this is our peak intensity here, I naught. This is peak intensity. All right. Moving on to the electromagnetic spectrum. So this is a really good representation of the electromagnetic spectrum here. So we have a few different things I wanted to point out. So we have this one here, this top piece tells you if it penetrates the Earth's atmosphere, so can it come through our atmosphere. The next line down is the radiation type. Okay, so we have 1, 2, 3, 4, 5, 6, 7 different types. We have radio, microwave, infrared, visible, ultraviolet, X-ray, and gamma ray. We have their approximate wavelengths below that, their approximate scale, their frequency, and the temperature of bodies emitting this wavelength. Okay, so for every single electromagnetic wave, we have this relation that holds true. The speed of light is equal to the frequency times the wavelength. Okay, so the greater the frequency, the smaller the wavelength, and vice versa. If we increase our, let's see, if we think about it this way, if we increase our frequency, we then must decrease our wavelength. If we do the opposite, if we decrease our frequency, we must increase our wavelength. Okay. For just understanding here, we see visible light. Okay, humans can only see visible light. And to put this into perspective of this electromagnetic spectrum here, if the spectrum represented or spread out along 3,000 miles, the portion that humans can see is only about a width of a dime. Yes, a dime. So we can only see just a smidge of this spectrum here. And what's interesting is thinking about why can humans only see the visible spectrum? Well, if we look at our sun is approximately, I want to say, about 5,000 degrees Kelvin, somewhere around there. So if we look at our temperature down here, 5,000 degrees Kelvin will probably be somewhere, I don't know, here, right? Something along those lines right there, which makes sense because look at that, it's about yellow. It's like yellow-orange, right? So our sun emits this color, okay? And so we will approximately see or our eyes, I'm sorry, our eyes will evolve to see mainly that color, right? Or that, I should say, that electromagnetic wavelength. I shouldn't say color, the wavelength. Okay, so humans, let's see, humans see visible light mainly. The sun is around 5,000 to 6,000 Kelvin. It's somewhere in there. I can't think of it off the top of my head. So we have evolved to see mainly our visible light. Okay. All right. So a bit more about this spectrum. Radio waves are quite large. You can see that they are the size of buildings. Okay. That is their wavelength. The microwave is a little bit smaller, about, let's see, 10 to the negative 2. That's about a centimeter, right? Then we get down to infrared. It's comparing itself to a needlepoint. Then we have visible light, which is what we see. Ultraviolet light is the size of molecules. X-rays, atoms. Gamma rays, atomic nuclei. Okay. So we have all of that information. We can look at the relation, like we were earlier, between the wavelength and the frequency. So we have a large wavelength here, right? The size of buildings. And our frequency is 10 to the fourth in hertz. 10 to the fourth hertz. Go over to the other end of the spectrum where we have a wavelength of 10 to the negative 12. Oops. For gamma rays. 10 to the negative 12. Okay, that's our wavelength, so quite small. Look at the frequency though. Our frequency here is 10 to the 20th power. Okay, so 10 to the 20 hertz. Okay, so you can see that relationship here. Now, I want you guys to understand the idea behind the electromagnetic spectrum and how to read it. If I give you a certain wavelength, I want you to be able to calculate the frequency and vice versa. Understand what humans can see. Okay. What else would I ask you? Maybe a little bit about the temperature, but not a ton. Okay. Maybe the main idea, is it colder or hotter? Let's see. I can't think of anything else at the moment that I may ask you, but just understand this spectrum. This spectrum really is important for us to know, and we'll look at it again in class. Okay, so if you have any questions on this, please feel free to let me know. This is something that is going to be coming up. Okay, all right. Next time we will talk about optics. We'll start that. But for now, we will be working on our electricity and magnetism, finishing that up, and then starting on optics.